Okay. Today is my great pleasure to introduce Kevin Buzzard. He's a professor of pure mathematics at Imperial College. He received the Whitehead Award for his distinguished work in number theory in 2002. He also received the Senior Barrick Award in 2008. He's a number theorist. He's also interested in formalizing mathematics, AI for math, and how technology can improve math education. Kevin is extremely popular with his students. I met him and many of them last year at Flock. As a last remark, as many of you know, Daniel Selson is starting the International Mathematical Olympiad Grand Challenge, where the goal is to get a gold medal in this challenging and prestigious competition. A few weeks ago, Madan found out that Kevin is a master puzzle solver. He got a perfect score when he was a student, a gold medal, and today Daniel and I had the pleasure to see him in action solving some of these puzzles, and it was human ingenuity at its best and how many magical steps are needed for solving the problems in this competition. The competition has 6 mathematical puzzles. Only the top students participate, and many of them can solve only or 2 of these problems. If you think Go is hard, it's a finite action space. In this competition, it's an infinite action space, and with many magical moves that demonstrate human ingenuity. Today, Kevin is going to talk about the future of mathematics and how technology is affecting it. Thank you.
Thank you for the invitation. Thank you, Leo, for the introduction. So, as he says, I'm a professor of pure mathematics at Imperial College London. I'm an algebraic number theorist. I have no background in computing at all. I've used computers completely informally. I've written Python code to solve games on my phone and things like this. But no programming background at all. I've used computer algebra packages. In particular, I've used Sage, written by William Stein, who's here with us, to do calculations, to do computation. I want to check 1 million examples of something. But really, I'm interested in theorem proving. And there's theorem proving software nowadays. And I work in a regular maths department, and no one in my maths department has heard of this theorem proving software. It even has theorem in the title, some of its stuff. This is supposed to be for mathematicians, but no mathematicians use it. So in some sense, the most surprising part of the slide is that a mathematician actually started to engage with this software. And all my colleagues thought I was mad. So I started goofing around with the Lean Theorem Prover, which is the software that Microsoft, that Leo has written, that Microsoft Research has written. And the reason I did it, I'll get to it, but the reason I did it was because not for my research, but because I was interested, because I was given an introduction to proof course to teach. I was told to teach the basic introduction to proof course, and I started thinking about what a proof was. And these computer theorem provers have an extremely precise definition of what a proof is. So that was how I got interested, because of an educational, for educational reasons. And then it slowly dawned on me what this software can do, and now I'm absolutely convinced that this software has an integral part to play in the future of mathematics. So many of my peers don't think this yet, but many of my peers don't. I think it's inevitable. That's the point. And I think it's only a matter of time before mathematicians start waking up and smelling the coffee. There's many theorem provers, and I'm not saying this because I'm here. I might be here because I believe this. That might be more likely to be true. But I started using Lean 2 years ago, but 6 months ago I thought I should probably try and look at all the software available. And I looked at all the software available, just with this one goal in mind of doing all of mathematics, somehow learning, attempting to do all of pure mathematics. And I'm absolutely convinced that if you want to do all of pure mathematics, then Microsoft is currently the winner. I think, hands down. I mean, that might not be true forever, But I think the lean, this is some technical issue to do with what kind of type theory it's using and how one can use it. But at the minute, I think you're sitting on the gold mine. But I'm not, in 10 years' time, things might be very different. So I'm not saying lean is going to solve all the problems, but tools such as lean are going to change the way mathematics works, and probably quite soon, right? Maybe in the near future, they're going to be helping us. How do you do search? As a mathematician, I have a technical, I'm doing my research, I have some technical question about very, very complicated objects. You can't Google for the answer to that question. Google is a useless tool. I mean, what's that? Bing as well. Probably these things just don't cut it. If I've got a technical question, has the following technical statement been proved? I know exactly how I'm going to answer that. I ask my friends. I ask my peers. And if none of them know, I ask the elders. I ask the experts in my area. Ideally, it would be nice to do that automatically. And this is one of the many things that I think that software might be able to do once we've made the database. I think also they can change the way we teach. Every year now, I get put in front of 270 undergraduates who've all just come out of high school, and none of them have got a clue. The vast majority haven't got a clue what a proof is, like a rigorous, logical, mathematical proof. They see heuristic arguments. They see, they're told that the derivative of sine is cosine, and the proof involves drawing a very thin triangle and heuristically arguing that if you have a very, very thin triangle, a triangle with an extremely small angle, then the two long sides are approximately the same length, which is intuitively obvious. But that's not the kind of thing you can type into the lean theorem prover. You see, so they come with a very vague idea about what a proof is and what they can get away with, and all of a sudden they find out at university that they can't get away with anywhere near as much as they used to be able to get away. It is true that the derivative of sine is cosine, but we feel that this needs a proof. And the proof that we're going to give them is very different to the proof. In fact, the proof I was told at school is circular, the proof that the derivative of sine is cosine, because it involves, you do the algebra and you end up reducing to the case of 0. You need to prove that the derivative of sine at 0 is cosine. So you have to compute sine of x divided by x and then take the limit as x tends to 0. And the proof of this involves somehow drawing the graph of sine and saying, well, it looks kind of intuitively obvious. And then you say, and actually later on we'll prove, after a while you forget about the question that the derivative of sine is cosine. The question is, what's the limit as x tends to 0 of sine x divided by x? And then once people have forgotten that was relevant, you sort of say, well, later on we'll prove that the derivative of sine is cosine. And so that means that this slope must be 1, because the cosine of 0 is 1. And somehow a circular argument is slipped in. So we get told rubbish at school, and then I have to pick up the pieces. And I got interested in lean because I thought it was... Because kids like software, right? I started 20 years ago. Kids didn't use software because there wasn't software. And now there's loads of software. And kids have computers in their pockets. And I figured, great, let's show them what proof is using software, because they'll like it. So that's how I started doing lean. And I think that this is almost certainly going to happen, and this might happen, right? I just don't know. This is your problem, not my problem. Can you actually start making these tools generate new theorems or generate new proofs? And I don't know, but then again, I've seen computers do things like beating humans at chess and beating humans at Go, and so maybe they can beat humans at maths. So I just don't know what's possible, but it would be very I want to be there when it happens. And I want to understand what's going on. So in April, I met this guy called Christian Szegedy at Google, and he thinks it's all going to, within 10 years, he says. He has a PhD in combinatorics, so he's an expert in a certain kind of maths. I've got a PhD in algebraic number theory, which is a completely different kind of maths. And I'm rather more skeptical. I think that when we talk about mathematics, we might be meaning different things. But he seems very bullish, and one of his papers has got 15,000 citations, so you've got to take him seriously. But he has a team that's, using Isabelle, not lean, using Isabelle, and he's going to do stuff. And I don't think Isabelle's good enough to do all. I don't think Isabelle is good enough to understand all of mathematics. but it might be good enough to understand all of what he thinks is mathematics. So that's the situation. So I'm just going to expand on various things. So who am I? I'm an algebraic number theorist. So ultimately we're interested in questions about the non-negative integers. And it turns out there are questions like Fermat's last theorem, which are very, very simple to state and extremely difficult to prove. This took us 350 years between the statement and the proof. It's very, very it's an innocuous-looking statement. It's completely of no use to anyone. This is, it's a puzzle, but it's just a great example of something that turned out to be extremely difficult. And I'm very lucky because while I was a PhD student, my advisor and his advisor proved it. So I was all of a sudden in the middle of everything. I'd learned a whole bunch of techniques that turned out to be suddenly extremely fashionable because mathematics has fashions. Right? I learned a whole bunch of techniques, and all of a sudden they were extremely fashionable. And hello.
Hey, do you trust the proof?
Oh, I've read the proof.
And it's good?
It's fine.
I was always worried they're so complicated.
Yeah.
That it takes someone like you to
Takes an expert.
say, oh, it's right.
Yeah, but there's loads of us.
A circular argument slipped in.
No, there's loads of it. I read the Wiles and Taylor work, so that part's fine. But there's 50 references.
But that's where lean can help, right?
I mean,
Write it in lean.
Yeah. So let me fast forward a little bit. How does the proof of Fermat's last theorem go? It breaks into two steps. Firstly, you prove that the semi-stable Taniyama-Shimura conjecture implies Fermat's last theorem. And secondly, you prove the semi-stable Taniyama-Shimura conjecture. Right, that's the strategy. And now the big problem with software as it stands is that even though it's existed for 30 years, this theorem-proving software, nobody has got round to even stating the semi-stable Taniyama-Shimura conjecture. So we can't even write the first line of the proof currently. And these things have existed for 30 years. So the proof of last theorem is structurally complex. It involves, even though it's a statement about non-negative integers, the objects that are involved in the proof are incredibly complicated. Like they take pages and pages and pages to define. So we've had to invent complex structures in order to prove a simple-looking statement about simple structures. And that's a sort of a general phenomenon of mathematics. Mathematics is, number theory is just undecidable, right, in general. And so certain simple questions about the natural numbers you can solve easily, and then somehow you have to. I think this is somehow this is part of the nature of mathematics. That there are some statements which are easy to state but hard to prove, and then there are some statements which are easy to state or impossible to prove. But the proof of Fermat's last theorem is long, you pointed out, but that's nothing compared to what we're doing nowadays because people are collaborating. It's easy to pass LaTeX documents around. People just write 200-page proofs, stick them up in the archive, and they look very professional because they're all written in professionally typeset software. And the moment they're on the archive, other people can start citing them, even though they've not been refereed. If you trust the authors, why would I cite a paper on the archive that hasn't been refereed? One of two reasons, right? If I trust the author, I'll cite it, and if I'm desperate for the result, and this is the only reference I know, then I'll cite it. But who cares if anyone's checked it? Because the currency, our currency is theorems. We want new theorems. So I started to get nervous, and that was another reason. Nervousness about the reliability of the literature was one thing that started making me think about using theorem provers, and then being told to teach a course about proof made it actually happen. So very briefly, the background. People told me that Haskell was I knew some Python, but people told me that Haskell was cool because it was completely different. I tried it, but I didn't get it. And then I was given this course to teach. And so then I thought I should go back to Haskell because it was it was more mathematical. I don't know. I tried again. The second time I did very well. I read this Learn You a Haskell for Great Good. It was the second time I managed to get through it. It's hilarious. And then somebody asked some question about, this is a fancy theorem in mathematics. The odd order theorem is a theorem with a very long proof, and it was formalized in a rival system, a system called Coq. And the proof was formalized. It took years to do. And I thought, this is kind of cool, because that's a relatively respectable theorem, the odd order theorem. It got John Thompson a Fields Medal. The proof is quite low level. The the odd order theorem is a question about finite groups, which are relatively simple mathematical objects. And the proof is lots and lots and lots of arguments involving finite groups. So it's different to Fermat's last theorem. Fermat's last theorem is a question about numbers, but the proof involves lots and lots of complicated structures. This involves lots and lots of ingenious arguments about finite groups, and it's a theorem about finite groups. So I goofed around with this, and I thought, yeah, this is kind of nice. There was a tactic framework, and I could prove simple, the kind of things I wanted to teach my undergraduates. And then Tom Hales gave a talk in Cambridge in 2017, which was live streamed by the Newton Institute. These are links, by the way. If I distribute the PDF afterwards, you can click on these links. And Tom Hales announced that he was going to make a gigantic mathematical database that had all of pure mathematics in. And he didn't name any software by name. And at the end, somebody asked him what software was he going to use. And he said, my proposal is Lean. And I thought, I've never even heard of Lean, but I trust Hales. So I thought, let's forget Coq, let's learn Lean. So by this stage, I'm convinced that one could try and formalize all of math. I've seen what Coq can do, and I've realized that all the mathematics I know is just kind of based on logic, and Coq understands logic. So I think, yeah, why not? Let's formalize all of mathematics. It sort of sounds like an interesting project. And so because Hales chose Lean, I think, right, I'm going to choose Lean. I'll give it a try. So Coq I tried and then I moved away from, but Lean I tried and never moved away from because it seemed to me to be the right tool. And now I believe it's the only tool that's currently available. I mean, other tools will, of course, appear. So I stuck with Lean, and now all I want to do, I don't want to do mathematics on pen and paper anymore. Because I don't trust it, and I don't trust other people that use it, which is everyone. I mean, I'm sort of having a midlife crisis. I think that's what's really happening. But, if given a choice between using free and open source software and buying a Ferrari, this is somehow a cheaper option. So I'm gonna stick to Lean, and now my job is, because I'm sort of one of 3 mathematicians in the UK that's heard of this. By mathematician, I don't mean these people doing category theory and type theory. People that say they're mathematicians but are proper mathematicians regard with deep suspicion. When I say mathematician, I mean a proper mathematician, someone that does like topology or analysis. None of these category theory people. These people are dying in my country. They're retiring from maths departments. They're not being replaced. They're finding their way to other. They're being hired by computer science departments, philosophy departments. But for 20 years, we had no foundational people at all at Imperial. And the foundational people that taught me in Cambridge, Peter Johnston, who wrote some book about topos theory, he wrote the Bible of topos theory. He's retired and he's not been replaced. We don't care about these silly, we don't understand logic. There's no point in logic. Somebody checked that logic worked for mathematics, and so now we can just get on with our mathematics. That's how we proper mathematicians think about it. So I'm one of, 2 or 3 proper mathematicians in my country that knows about this software. And because I think it's going to turn the entire world upside down, I think it's my job to try and tell them about it. So let's start with the undergraduates. I love teaching. Both my parents were teachers. So I thought I'll try and teach the undergraduates to use this software. That was the plan. So I just kind of threw myself in. I started a blog. Yeah, I'd never done anything like that before. I'm on Twitter and started an undergraduate club and sort of basically said, come along and we'll figure out how to use this software together. And because I'm a very visible lecturer, all the students know me because I've been teaching this first year course for several years, and it's a compulsory course. So I can, if I tell a bunch of students to go and do something, a lot of them will do it. So I said, come to my club. So like 70 people all show up this first week, and then we realised that actually this software is really hard to use, and we don't quite know what we're doing, and it is a very high entry bar. So lots and lots of people came in week 1, and by the end of the semester there was about sort of 6 people coming, and then by the beginning of the next semester there was about 2 people coming. And so the 2 people were Chris Hughes and Kenny Lau. And what was quite funny was by February they were both better than me, because they're young. I'm 50 years old. I learn things. I can still learn things, but it just takes me some time. I have to be told things 3 times before they sink in. And I'm not used to undergraduates being better. I'm shit hot, right? I'm an expert puzzle solver. I'm a professor of algebraic number theory. I spend all my time dealing with these undergraduates, and they can never tell me anything I don't know, right? That's been true for 20 years. I dominate the undergraduates. They can ask me the hardest question they come up with, and I can answer it because I find the material trivial. And for the first time in my life, undergraduates are telling me things that I'm interested in. So I thought this was really interesting from a pedagogical point of view, is that I'm actually trying to use this software and I'm getting stuck, and they're telling me, they're telling me the way I should be thinking about mathematics. So this was extraordinary. And these 2 people somehow ended up, one of them is now a maintainer of Lean's maths library. And these people are very smart. So 2 years ago, neither of them knew anything about type theory or computers or anything. They were at school. And now they're writing professional software. They're writing PRs. They've written 30,000 lines of professional code. So I think that's kind of weird. So then my institution started noticing that I was doing something a bit strange. They have a pedagogy transformation grant. They have money for summer projects. And I've got 3 kids. I'd spent 20 years never doing any summer projects because I was having to babysit. My partner's a surgeon, so she's very busy. So I would babysit because I'm an academic. I would just take the summer off and do the childcare. My kids are all teenagers now, so for the first time last summer, I thought I can actually go to work during the summer and just leave them at home and just hope they don't burn the place down. So because I'd spent 20 years doing no summer projects at all, I said, I'll do 20. Will you pay for them? And Imperial came up with money to pay for 20 summer projects, and all of a sudden I had 20 undergraduates. And I said, right, let's just digitize bits of the curriculum. Take any piece of maths that you thought was interesting. Let's type it up into Lean. We had a really good time. And then October 2018, the new first years come in. I'm teaching my course again, and I've got this kind of group of 10 students that actually know what they're doing. So we got 70 people in week 1, and then I got like 50 people in week 2, and the students are talking to each other, which is perfect, about mathematics. So the surge took a lot longer to die down, and now there's a kind of a core group of 10. By the time, when the exams come, then it's only the hardcore people come. So I'd gone from 2 hardcore people to 10 hardcore people, and in October it's going to start again. And now I've got lots and lots of people that know what they're doing, including several people that know what they're doing more, better than me. So that's what's happening with the undergraduates at Imperial College London. And what have they actually done? We arrived at a perfect time because Lean had just got all the prerequisites available to start doing mathematics the way a mathematician does, pretty much. Not quite. But, things like a theory of finite sets that we think of as trivial. It was, thousands of lines of type theory code was there in the maths library already. And so I just told the students, why don't you just take some random undergraduate piece of maths and formalise it? Because this is all undergraduate level mathematics. And none of it was that. The complex numbers weren't even in Lean when I started. My first achievement in Lean was to define a complex number as a pair of real numbers and then prove basic facts about the complex numbers. And I'm just thinking, if I can do this, I can do anything, because that's exactly how I think about mathematics. So I just said, take a random theorem, why don't you prove it? Some of these theorems are quite hard to prove. Some of these are substantial pieces of work. But they're all done, and the undergraduates did it with very little help from me, really. They just kind of got the hang of it, and they talked to each other, and they worked it out. And this software's been around for decades, but as a teacher, I'm interested in, where's the undergraduate mathematics degree? That would be, for me, a very natural thing to formalise. And it's not there in any of the systems. People just do bits and bobs. They kind of choose an area and they do that. Why can't we have one coherent body where all of the mathematics in a normal undergraduate degree is there in one library, or at least in one system? 30 years this software's been around. No one's ever done that. The proof of the odd order theorem, they needed bits and bobs from an undergraduate curriculum. They needed the third-year group theory course and the third-year algebraic number theory course, half of the third-year algebraic number theory. So they formalised those bits, but they're not trying to make a library. They were trying to prove a theorem. So they just They did bits of it. Whereas it's just a different way of doing things. Why don't we just digitise our curriculum? The students, I don't know what that will achieve. It'll be fun, right? It might teach the students something. I don't know. It might create an object that's never been created before. I'm a blue sky researcher, right? That's great. I do normal proposals. I say I want to prove some theorems in the area that we're all proving theorems in. I want to prove similar-looking new theorems. I think this is much more exciting. I want to make a new object. I want to make an undergraduate degree. So there you go. So here's some undergraduates. I'm at a really cosmopolitan international university. Ellen is German. Sang-woo is Korean. Kenny's from Hong Kong. Guy is French. Amelia's British. Jean's from Taiwan. Rohan's Australian. Blair's Chinese. Abby's Indian. Call's Swedish. All these people have written code that's now in Lee's Maths Library. All these people, and every single one, without exception, none of them knew a damn thing about type theory or, coding or anything. They're all mathematics students. And I've taught them all to write professional code. And these people here, Sean, Anka, Clara, and Ramon, they've done projects with me. This is Ramon's MSc project was formalising the definition of a scheme, which is an MSc level mathematical object that was in no system. 30 years we've had this. Fundamental. Vladimir Voivodsky got a field medal for proving a theorem about schemes. And then he went off and invented univalent type theory. And 10 years later, had he formalised the definition of a scheme? No, he hadn't. I mean, what is going on? An undergraduate, an MSc student formalised the definition of a scheme. And then I started looking around, seeing how it was done in the other systems. And I found that it wasn't there in the other system. This is publishable work. So it's 4 author paper, me and 3 undergraduates. Because I formalised it with 2 undergraduates in a poor way. We made some poor design decisions because we're amateurs. And once I'd learned how we should have done it, I gave it Ramon as an MSc project to fix up, to do what we should have done. And I'm collaborating with undergraduates. Maybe that's normal in computer science departments. That's absolutely unheard of in pure mathematics because we dominate the students. They have to be doing PhDs before they can even get to the point where they're asking questions which find interesting. So this is very strange for me, and very exciting as well as an educator. So I've written a piece recently in the London Maths Society News. Within the UK is sort of a small place, and I'm a known person. And I was asked by the London Maths Society if I'd write a piece for their newsletter about your software, and I did. It's a small 5-page thing. But I talk more about undergraduates there because I figure that a lot of general mathematicians in the UK reading this will not be so interested in my great research or whatever, but they might be interested in teaching because that's what's paying the bills for us. So what do the undergraduates not like? They're smart, the undergraduates in my university. They got the hang of the software, but the documentation's hard to read because it's written by computer scientists for computer scientists. So somebody needs to write documentation that's more mathematician appropriate. So I can do that. I just haven't done it yet. And the other thing is they all use Windows laptops. They all use typically cheap Windows laptops. And to install the software, they need to install a command line and type things like git clone or something. These really exotic commands that mathematicians are never. We don't use computers. We don't use anything. So I had to one of the major parts of my job over the summer was to teach 20 undergraduates how to use Git. This is because it's a really, really essential tool, which is not taught. It's not taught. And to use Git, it's just sort of ridiculous. The easiest way to compile Lean is via the command line. You just download some compiled binaries using some command line. So I don't know. I got a bit frustrated after a while, and we used something called CoCalc instead, which works really well. This is multiplayer Lean. VS Code has some multiplayer option, but it doesn't work with Lean. Did you ever try using multiplayer Lean? In VS Code, several people can edit a file at the same time, but the Lean server is only running on one computer, is running on the host computer, and the guest computer can use the server, but it can't import. All the imports fail because it attempts to do the imports locally, and then there's some compatibility issues. CoCalc has solved all these, so I've run kind of multiplayer CoCalc webinars where we go through a file and we all edit it together. It works really well, but you have to pay. And so and I can't pay for 270 undergraduate licenses. I mean, I could ask my department to, but my department's already given me, tens of thousands of pounds. I mean, they might buy it. Well, one thing I've learnt is that you can engage undergraduates, and even with no programming background, you can teach them. It's exhausting, but you can teach them to use this software. And the other thing that my department did was I asked for a specialist in education to come and examine what I'm doing. Because I was giving lectures, but the last year I gave this course, I would fire up Lean and I would state theorems, and then I would prove them in Lean. And I would give out notes that had the traditional PDF proofs, but I would do live Lean coding in lectures. And these people watched what I was doing, interviewed 40 of the undergraduates, did surveys, and are currently writing an education paper about my intervention, as it's called. But it's not ready yet. It's coming out beginning of October, apparently. They've been very tight-lipped about what they're going to say. I don't really know. They might just sort of say, this guy's an idiot, right? I don't know. But who knows? But it, it'll be interesting to see what happens. And so my course starts again in October, and now I know what I'm doing. So all the notes will be formalised. All the problem sheets will be formalised, and they will simply have a choice. You can do it in the old-fashioned way, with pen and paper, or you can do it on a computer. And the course has been reorganised. Other people are teaching parts of it, and I took precisely the parts which are sort of the maximally easiest and funnest to do in Lean, and we're going to do those first. So the first 8 lectures that the new undergraduates in my university, the new maths undergraduates will see, will all be given by me. There's just going to one course, and it's my course, and it's going to be heavily Lean related. And we'll just see, right? We'll just see. And what the notes will look like is a guy called Patrick Masso in Orsay. Where are we going? It's here somewhere. Oh, here it is. He's already done this. He gave an introduction to proof course as well. There's some basic stuff about equivalence relations. But down here, here's a proof, and you can fold everything up, and then it just looks like a normal mathematical proof. But then you can unfold things, and you can see the state. You can see the tactic state before and after. So there's before, and there's after that next line, and there's after that next line. And what I've learned very quickly is that mathematicians find this extremely hard to follow because these are Lean tactics. It's language specific, things like this. Quotient exists rep. Students find this hard to follow, but students, within a couple of hours of my course, students can understand what's going on here. Because this is just normal mathematics. It's all done in Unicode, which is crucial, really. Students understand what this says with very little training. And even if they can't follow this stuff, you can just keep clicking on these grey things here, and they can watch the tactic state change, and they can follow it, and they can see what's happening, and they can begin to learn what a proof is. So that was one of the reasons I got interested in Lean.
So who put this together, this literate proving?
This is Patrick Masso wrote some Python code which takes a Lean file with comments, but the comments are written in LaTeX.
Yes. Okay.
So this is the source code for this is a Lean file which compiles and runs with comments written in LaTeX, and he runs it through some Python code, and it produces a web page that looks like this. So that problem is solved. And so that's great for me because I just need to type up my 8 lectures in Lean, put comments in LaTeX, which I can just knock off very, very quickly. And then you compile it, and then I have this. And that's what I'm going to be showing the students. And it won't be in French. Even better. So there we go. So there's the undergraduates. And as I say, I'm convinced that it shows them a new way of thinking. It turns proving into a game, right? It turns proving into a game. That's what it is. And games are great, right? Kids, if you watch the students, when they finish doing maths, they play games. They play games on their phone. They play games on their PC. They play nerdy games. They play Minecraft. They play all sorts of things. But that's what I think. That's how I sell this software. right? It's something I need to teach, but I'm turning it into a game so it's more fun. And then, as well as that, I want to digitise the curriculum. So in 3 years' time, when we're finished, because it's ticking along, we'll be able to say Imperial College, all theorems formally verified in Lean. It would be a cool thing. Okay. This is the first. This is me 2 years ago. First question on the first example sheet. Is it true that if x is a real number and x squared minus 3x plus 2 is 0, then x is 1? The question has an implication sign in. X squared minus 3x plus 2 equals 0 implies x equals 1. So I failed to typeset the main point of the question. There should be an implication sign, because I'm trying to teach them what that symbol means. X implies y. So what I expect the students to say is, no, this is not true, because x can be 2. So you type that into Lean. If you're me 2 years ago learning this stuff, you say x equals 2, and then Lean says, great, so now you've reduced the question to proving that 2 squared minus 3 times 2 plus 2 is 0, and now you've got to prove that 2 isn't 1. So as a student, how are you going to prove that 2 equals... This is impossible, right? Because this is a quotable fact. So then and initially I was thinking, this is a flaw with my plan, because now the students are going to say this software is stupid, because how does it not know that 2 isn't 1? But now I've turned that around. I say to the students, well, how do you know that 2 isn't 1? Is that an axiom? Like 53 isn't 28. Is that an axiom? Is that a rule? Is that a theorem? What's actually going on here? Initially I thought the software was just being annoying, but now I've realised that actually there's a pedagogical point to this now. I'm showing the students that the things they thought were obvious about the real numbers, we need to find a way of justifying it. And there's a tactic that solves these now. When I ran into this issue, I couldn't do anything. I mean, I was stuck. And I asked on the Lean chat, and they're like, oh yeah, that's quite hard, because the real numbers are really complicated. If these were integers, it'd be fine. But unfortunately, I've asked a question about real numbers. Last year, I changed the question to add x an integer. But this year, I changed it back again to let x be a real number, because now we have the tools to do this. There's tactics that resolve questions like this. So I raised this on the list. I said, undergraduates can't use your software unless this can be made easy. Mathematics undergraduates can't use it, and so it was made easy. So students went really well, and I love students, and that was really great. So now what about the staff? So initially they were just like, oh, kind of Kevin's doing a stupid thing. Kevin's doing something we don't understand. But I started telling people about it, like how this was going to change the world, and we should all learn it, and it's very important. And again and again and again, I get this question, can it actually tell us anything new? Because that's what we're interested in. We're not interested in the odd order theorem. That's old. We're interested in new theorems. So where are the new theorems that this software is generating? And my answer to this always used to be no. And I've realised that that's not a very good answer. It doesn't sell it very well. So I've changed my answer. And now I say not yet, which is also valid. It's equally true, but it's a lot more positive, and it more accurately reflects my beliefs. Not yet. But it's still enough to make 90% of people stop listening instantly. Because that's what mathematicians want. They want new theorems. That's what excites us. So there we go. There's this other system called Coq. It's it's an older version of it. It's the same type theory as Lean, but with more design errors. Lean, I guess, learned a lot from Coq. So there's this proof of the four-colour theorem, which is this famous theorem, because the proof was weird, because it was like thousands of special cases, and mathematicians were uncomfortable about it. Then there's this odd-order theorem, that's also checked in Coq. The proof of this is low-level. There's hundreds and hundreds and hundreds of theorems about finite groups put together in a clever way. So this has been formalised in Coq, and the conclusion from this is that the software can handle theorems which take hundreds of pages. These theorems are hundreds of pages long, and the software can handle it and compile it, in an hour or two. The software is ready to handle proofs which are hundreds of pages long. That's an important data point. This work is phenomenally important because it means that the whole thing is feasible. And as I say, these have been formalised in some older software, but if Coq can do it, then Lean can do it. I don't know anything. I don't know anything that Coq can do that Lean can't, in theory, do as well. But why aren't people interested? And one reason is because we don't care about the odd order theorem, because it was proved 50 years ago, and 10 years after that, they proved the classification theorem for finite simple groups, which answered the big unsolved question about finite groups. And then everyone left the area, and the area became dead. So the area's been dead since the 1980s, and then in 2012, all these computer scientists are like, oh, we formally verified the odd order theorem. We're like, there's nobody left who's interested anymore. They've just gone. They've retired and gone. The area is dead. We care about fashionable mathematics, and finite groups are no longer fashionable. In some sense, this was a very poor choice, but in another sense, it taught us a lot of things. But I'm interested in marketing, right? I'm interested in marketing your software to my people, and this is a poor choice. And the other thing, of course, is that we're also sufficiently arrogant. We know what a proof is, and a proof is if the elders say it's okay. Right? And do the elders think that this proof of the odd order theorem is okay? Yes, they do think it's okay. They gave Thomson a Fields Medal, right? And that's it. The committee of elders gave him the Fields Medal, and so we're there, right? That means that the proof is accepted. Who cares if it's correct? The question is it accepted? That's what we want to know. And this theorem is accepted, so we don't care if it's correct, because it's good enough, right? And it's correct. Sure, it's correct. We all knew it was correct. Because everything that's accepted is correct, apart from the small number of errors that we've made, right? And we don't know where the errors are, but history says that the number of errors we've made is extremely small because we're good. We're mathematicians. We're good at smelling problems. If some argument doesn't quite look right or looks incomplete, or your gut feeling is that what's known isn't going to be enough to prove that result, then you can smell it. And if you smell a bad smell, then you've got this 200-page paper, and you don't read it from the beginning. You start looking at the statements of the lemmas, and you go, I believe that, I believe that, I believe that. Ooh, this looks optimistic. And you read that lemma very, very carefully. And if the proof is fine, you've learnt something. If the proof isn't fine, you reject the paper. So we're very good at reading gigantic papers in an extremely non-linear way and trying to work out what's right or not. So we knew this was right because this was read by hundreds of people. And, I think there might be some problems, but I don't think it's all wrong. And I think that the chances of something big that we believe turns out to be wrong, I think is actually quite small. So I don't think that's the way of selling this software to mathematicians. So Fermat's last theorem, the statement is trivial, but what does the proof look like? First, we spent 300 years fiddling around inventing algebraic number theory, basic algebraic number theory. And that gets us to the early 1900s. Then by the 1930s, we invent elliptic curves and modular forms. And then we invent 10 other things. This is the 60s, 70s, and 80s. And then we start... each definition relies on earlier definitions. And so by the end of it, some of these definitions are huge. And then we put all of these things together. So 350 years so far. We put all these things together, and we get it. But now here's the problem, is that I can't get my undergraduates to do this bit. Because this is what you learn when you're doing a PhD. I can't get them to formalise the definition of a p-adic Galois representation because they don't know what it is. And my experience is that you shouldn't try and teach somebody some new, interesting and complicated mathematics while simultaneously getting them to formalise it. That's the thing. You should get them to formalise stuff that they understand. That's what works best. First they understand it, then they formalise it, and then they really understand it, and it sort of stays forever. So this is just too much. I could spend a year supervising an MSc student to learn what these objects are, but then we've got no time for the formalising, you see. So the proof goes like this. You invent all these complex structures, you prove some relationships between them, and then the theorem just comes out in the wash. That's how it works. That's what mathematics looks like. You invent sufficiently complex tools, and then you let the tools do all the heavy lifting for you. So the proof, of course, takes thousands of pages, and no one's really read it. So there you go. Could we formalise it? Here's a project. Why don't I formalise? I know the proof, or I know bits of it. I know the Wiles-Taylor part. I don't know all the proofs of all the references. Well, I formalised the proof. I could lead that team. I've led teams before. I built up number theory from nothing in London. I could build up this stuff here, but it will cost a huge amount of money. And it will cost a huge amount of money. And the problem is we don't care because the elders have said it's fine, right? The elders have said the proof is fine. So what's the point in checking it? So there's one obstruction to doing it, is that no mathematician sees. So no agency that funds mathematics will fund it either, because how does it work? I send my proposal off, and then they send it to mathematicians, and the mathematicians are like, what's the point of this? There's an absurd amount of money to do something that there's no point in doing. So that's not the way to sell it either. Okay, we don't care because the elders say it's fine. We know it's fine because we gave Wiles a prize. And it's interesting because no human actually understands it. Mathematics is quite modular. This is a sort of side remark. No mathematician understands the proof of Fermat's theorem, the full proof. I mean, many of them have read Wiles's paper or the references, but I've never read the proof of the Langlands tunnel theorem because it's just a lot of harmonic analysis. But I understand the statement, and I can insert the statement. You know, I can apply the statement, but I don't know the proof because I don't know enough analysis. I'm an algebraist. So the proof is modular, and different people that we trust in the community have verified different pieces of it, and so now we say it's fine. And it's getting worse. As I say, nowadays people are verifying proofs where, you know, so if an elder says, and this is forthcoming work, but I'm putting it on the archive now, that I know 2 instances just in the last couple of years where people have brazenly said there is 100 missing pages, literally 100. I've asked authors, you say this is forthcoming work, how long do you think that work will be? And when is it going to appear? And I've had 100 pages, just missing stuff. And it's fine, right? It's the way the system works. It's the way the system works. And it's difficult to disrupt that. I say, look at that, is this really fine? Are we actually doing mathematics? And the answer is yes, of course we are. That's how it's always worked. It's fine, they will appear. But in 10 years' time, those 100 pages will probably have been written by some poor PhD student or postdoc. You know, it's a tedious technical result that everybody knows. All the experts say the techniques are there. What's even the point of writing it? We'll get a PhD student to write it. We'll teach them the area. You know, it's an efficient way of going about it. So it's sort of funny. And I'm beginning. And do you trust a PhD student? I don't know. I because I'm getting a bit paranoid. I'm sort of not. That's not the way to sell. That's not the way to sell the software. So we accepted the proof in 1970. We gave John Thompson a Fields Medal, and that's why we know the order is true. We don't care that it was formally checked in Coq. We don't even understand what that means. 99% of the people I work with don't even understand what that means. We formally verified the proof. Because they don't know set theory. They don't know what, you know, they just do mathematics the way Gauss and Euler did it. Gauss and Euler didn't have axioms and foundations, and they were still doing mathematics. We're doing it like that still. You know, the set theories check that there's some way of making it work with foundations, but we don't care. So they don't really know what the thing means. So what are we interested in? We're interested in perfectoid spaces. That's what we're interested in, which are fancy new objects, which were made about 5 years ago. So here's the table. There's the proof of the odd order theorem. That was what you guys thought was going to be exciting. That's the thing that really is exciting. They both got Fields medals, but where have they gone, right? No one in my department knows anything about the odd order theorem because there's no one doing finite group theory anymore. But my PhD students all know what a perfectoid space is, and so do the PhD students, the person in the office next to me. Perfectoid spaces are exciting, right? I formalised a scheme. That was 50-year-old mathematics. I was like, this is great. This is MSc level mathematics at a theorem prover. And I talked to algebraic geometers, and they're like, I learned what a scheme was when I was an MSc student. And I realised I had to go higher. So perfectoid spaces are vastly complicated mathematical structures. And we did it. I thought, let's really learn how. This is what taught me how to use the software in a serious way. Me and a topologist and a postdoc in number theory, all of whom I met online in the Lean Theorem Prover chat. All of us are mathematicians. It took us 8 months. We formalised the definition of perfectoid space. It's like 10,000 lines of code. They love it. Mathematicians love it. They don't understand it, but they know it's different. So I get invited to give colloquia all around the place. It's absolutely great. Up and down. Hi.
So does that build on a whole bunch of other stuff you haven't formalized?
No, it builds on a whole bunch of other stuff that we formalised, and that's why it took us 8 months.
So it goes all the way down to...
It goes all the way down to the axioms. All goes all the way down to Lean's Maths Library. We meet Lean's Maths Library.
Oh, okay.
So it's compiled. It's sorry-free. It compiles.
Okay, sorry for this.
And we had to formalise a whole bunch of Bourbaki general topology, you know, a very formal math textbook. The topologist did that, and then we did the graduate level number theory on top, me and the number theorist. This guy here is a postdoc. He's putting his job on the line here, right? This work. Who referees this? Somebody who understands type theory and perfectoid spaces. Who's that? That's me. That's me. That's me and this guy. And I don't think I'm a valid referee. We've written some weird paper that just falls between the cracks because, type theory is a big area, right? Theoretical computer science is a big area. Algebraic number theory is a big area. Number of people in both is tiny. So it's sort of fun. We don't quite know what to do with it. We're writing the paper, and we'll see, right? We'll write the paper. We'll stick it in the system, and we might just completely fail to publish it. But I don't care. If the computer scientists don't see the worth, I'm not targeting the computer scientists. You kind of get it. At least you understand what the software's doing. This is a PR exercise for me. I need to get more mathematicians involved because I have a vision. I have a gigantic vision, and I'm one person. Perfectoid spaces took 8 months. Do you know how many definitions there are? There's hundreds, there's thousands of definitions, right? This is both, right? I specifically chose perfectoid spaces because I knew that mathematicians found it sexy. And I was right. I formalised a perfectoid space, and I've done some stuff with undergraduates. I'm, great, let's give the colloquium. I'm giving the colloquium in Durham in 2 weeks' time, and in Exeter. I'm going length and breadth of the country. And in the EU as well, I've given a talk in Germany about it all. It's great. And I'm just basically being an evangelist for your software. It doesn't tell us anything, right? It's the first question. Does it tell us any new theorems? I'll tell you what it does. It enables us to state old theorems. We can state the theorems. Schultz proved a theorem about perfectoid spaces and got a Fields medal. Now we can state that theorem. But you can't prove it. Can we prove a new theorem? We don't. If you can't state it, where do you begin, right? Now we can state it. That's where you have to start. That's why I'm doing it. Because you have to start somewhere, and it's sort of ridiculous. And computer scientists say, you've made a definition. It's like I'm making a class. Lean enables you to reason about code, and you can prove a hard theorem. You can prove that this code does a certain complicated thing. You can prove a hard theorem, and that's a triumph. I'm just defining a class. Like, anyone can do that. Maybe I've made a mistake. Sure. But maybe the definition's not right. The definition's changed since it was made. It was tinkered with. And if it gets tinkered with again, that's fine. I'll just tinker with my code. I don't care whether it's right or not. We have something. So this is, let's skip this bit because I want to stop on time. The formalising definitions is difficult. Sorry? Hello.
So there's a problem of trust. Now, you trusted mathematicians, now you need to trust software.
Yeah, I trust software more than I trust mathematicians. It's as simple as that. Because I found mistakes. This is what's really going on. I referee papers, and once I had a really bad experience refereeing a paper. I spent 2 years arguing with the authors that their proof was incomplete. And eventually I won. But I was the referee. And this took a lot out of me. I had young children at the time. And it basically destroyed my... The authors were experts, and it destroyed my trust in humans. And my trust in Leo software has not yet been destroyed by any means. I think there's orders of magnitude. I think it's an order of magnitude more reliable. I don't care that it might not, I don't care that it's not 100%.
Lean doesn't have an ego.
Lean doesn't have an ego. So why do I want them to use it? Because I've got a plan, right? We need to, before we can start proving new theorems, we need to be able to state old theorems. And that's what we can't do, because we can't state the semi-stable Taniyama-Shimura conjecture, because we haven't even defined the definitions. So there's all the definitions. There's not millions. There's only hundreds and thousands, right? There's not that many. I've done one. It took me 8 months. I'm better at it now, though. It won't take me 8 months to do the next one. I've just written an EU grant proposal where I propose to do 10 more, right? But what you would love to do, really, is just feed in the book. Just take the book apart, feed in the PDF, let the computer read it, and then interpret the natural language, and then that's great. And that's a million miles away, I think. I'm not an expert in this, but my impression is that computers cannot read human-generated mathematics. I think you actually have to write it properly. And so to get mathematicians to do that, you have to teach mathematicians to write in this programming language. It's no good teaching them to write in English. You have to, and that's what I'm doing. And I can't really get the staff to do it yet, so that's why I'm getting the students to do it. But there has to be a new culture. We have to start making students write in this. If they want, they should be able to write in this language. Because I've got 1,000 definitions I want to do. It's maths and computer science. Like grant agencies should love this because it's synergy, right? But let's find out. Let's see if it actually. I mean, there's problems. So as I say, this stuff's been for 30 years. But if you ask a random mathematician in my department what they're working on, they'll state a theorem, and it would be impossible to state that theorem in any of these theorem provers because it will be about objects that computer scientists don't understand. It's as simple as that, because computer scientists are not research-level mathematicians, right? We're learning about p-adic Banach spaces, and we're proving lemmas about p-adic Banach spaces. There's no definition of a p-adic Banach space. So the software, it's been around for 30 years, and it still can't understand the statements of what we're doing. That's how far we are away. It's farcical. It's just farcical. 30 years. It's time we got together. It's time we got together. So we don't see the objects that we think are sexy. So I just written an EU grant proposal, 2 million euros to just give me a couple of postdocs who can just spend their time formalising definitions and formalising famous mathematical conjectures and famous mathematical theorems. And this has gone to the EU, and on the 31st of October, the UK is going to crash out of the EU with no deal, and my grant application will instantly become invalid. Because if we came out with a deal, we would be some kind of member, we would be some... If we come out with no deal, then my grant proposal has failed. So, but the idea is, like Trump loves Johnson, and the idea is that we're going to be friends with America now. So yeah, when we get, like, remember me on Halloween, because apparently America are our friends. So if you want to give me $2 million, or even $500,000, just to fund a postdoc, Microsoft-funded postdoc, who's just quietly going to come and work with me at Imperial and just change the world, that would be great. That would be great, right? And Tom Hales says we should make a database. And Tom Hales is a very smart mathematician. We should just make a database. That's where to start. Let's just make a database of mathematical objects, and then let's state the theorems that relate these objects to each other, right? I think that's the next thing you want to do, right? Lean is the right tool currently. Lean is the only viable tool currently to do this. Let's tell it what modern pure mathematics is, right? Let's not prove any more big theorems that are 50 years old. Let's just define some modern stuff, right? And now who's going to do that? People like me that know the mathematics, and people that I'm making, people that I'm training. I'm a professional trainer. I've graduated 15 PhD students, and I've taught 15 undergraduates how to write MathLib-ready code, right? I can train these people, and when we've done that, it'll happen somehow. And when we've done that, we can make a database of stuff and a database of links between that stuff. This implies this. Or, everything, every X with property Y is, gives us something with properties. We can just state the things that the elders believe. I don't care about proving them. That's harder. We can just state it, and then we've made a big database of our beliefs. We're writing down our belief system. And that database doesn't exist anywhere. This is a completely new kind of database. And then what we can do, we can start attaching things to the labels saying this was proved by this person in this journal. And then suddenly we can start searching it, right? Because you guys can do that kind of stuff. And then, we can start asking basic questions. I don't know what we can do. That seems trivial. And that will be great. That will make mathematicians in the third world, that don't have... I have access to the elders. Some of them work in the same building as me. But people that don't have access to the elders, they can use the database. Maybe we can make tools, undergraduates, if I can persuade the undergraduates to all work in this software, then I don't have to mark their work. Instant feedback, that's what they want. 270 students and me, I find it very, very difficult to give them feedback. This is one of the biggest criticisms of my university. Not enough staff, too many students. We love the students because they're paying our salaries. Too many students, and they want feedback. Right? They do some lemmas, they write some PDF stuff, they write some stuff on paper, it goes into the machine. A week and a half later, it comes back with some PhD student who's attempted to mark it, not always accurately. And they're paying £9,000 a year for that. And this gives them instant feedback. I think that's, I think that's worth something. And then of course, world domination, right? And then I can give up. That's it. Thank you.
Can you say a little bit about the features of Lean that made it well suited for this compared to the other systems you tried?
So I looked at four kinds of foundational theory. There's set theory, which is what all mathematicians, if they learn anything at all, they learn set theory. But the only software doing that, automation is very difficult with set theory. And I need automation. So I gave up on the set theory ones. There's symbol type theory, Isabelle, and the other big player really. In my mind, it's, and Isabelle, symbol type theory is too simple. It's really great for doing 100-year-old analysis. And it's really great for proving theorems about spheres and things. But you can't, you can. It would be extremely painful to define a perfectoid space in Isabelle because the fundamental object is a dependent type. There's a sheaf of rings on a topological space. So I've got a topological space, and for every open subset, I've got a ring, and this is a dependent type. And you do it in Isabelle. You do it in a simple type theory. You need a proper function. You can't have a dependent type. You need a function. So you take the disjoint union of all your rings, and now you've got an object which isn't really a sensible mathematical structure. And then you put ring structures on subtypes of it, and now all of a sudden you can't use any of the type class machinery because it's not actually a ring. It's a disjoint. It's a big collection of rings. So you lose the type class system. So I don't want to do that. It's fast. It's faster than Lean because it's simple. But and it's good for some of mathematics, but I definitely want to do all of it. So then there's univalent type theory. And I'll buy that, I think, in quite a univalent way. That looks sort of good. But they've been around, Voevodsky and his chums are around for 15 years, and you look at what they've done, and they've done nothing. They've defined a ring and a module. I don't see any... If it's taken them 15 years and they've done nothing, then I'm very sceptical. 15 years in Coq, they were really doing stuff. But Lean's maths library, when I arrived in 2017, that software's only a couple of years old, really, in its modern form. When was Lean 3 released? 2016. So within 1 year, the amount of stuff in Lean's maths library just completely dominated what had been done in 15 years in univalent. I don't know what's wrong with univalent mathematics. And of course, I hope that it will work, right? There's something else just happened. What's it called? AREND. Someone's made a new system. I would love to see univalence work because univalence is really useful. We have to work around the fact that we don't have univalence, but we can do it because the system is powerful enough to work around it. That was one of the mistakes I made in formalizing schemes, is that I just assumed that univalence was obvious because I'm a mathematician. I wanted to rewrite, X was isomorphic to Y, and I'd proved a theorem about X, and I wanted to deduce the theorem about Y. And then I was told that life wasn't so easy in dependent type theory. And that's why I started again. That's why I'd written this formalization of a scheme with 2 undergraduates, and I realized that we'd made some... we had to work around, we had to do a lot of diagram chasing. And then I gave it to another undergraduate and said, this is the mistake we've made, do it in a bit more of a universal property kind of way. And they did it and it worked fine. So it's just I have lots of evidence that Lean is good enough. Perfectoid space. So symbol type theory is too simple. Univalent type theory, it might work, but someone has to do it. And I'm going to do finite sets. Finite sets are trivial. But in Lean, they'd all been done for me by the people that came before me. I want to do proper mathematics. So no univalent system seems ready. And I think that's it. I can't think of any more. I need dependent types, and I need a sufficiently advanced system.
And you said
And this is
in terms of
Coq is just not as good as Lean. Coq doesn't have quotients. A perfectoid space is a quotient with a dependent type on it. That's the answer to your question. A perfectoid space is a quotient with a dependent type on it, and that hence immediately rules out Coq and Isabelle.
Why Coq?
Because Coq doesn't do... You can't really do you can't make the quotient. You can have a big space with a relation on it, but you can't make the quotient type. You just have to work with the big space and the equivalence relation. You're constantly jumping. You're in something called setoid hell. That's what it's informally known as. So, yeah, I don't know. And it's just, Lean is just sexier. It has Unicode. I want this, it's a ridiculous thing, but for mathematicians it matters, right? I'm coming from a different world where I'm trying to sell stuff, and it just matters that we have Unicode. Unicode is what we write in. We write upside down A's on our bits of paper in our PDFs. And that's what I see on the screen. Hello.
Speaking of Unicode, did you assess Agda at all as a potential tool for formalizing that?
I didn't. I was told that Agda wasn't really for mathematicians. I was told it was more of an experiment in type theory. There's no tactic framework, is that right? Is it just all terms?
Not that I know. It looks very different to something like Coq or Lean as well. I actually sort of loathe how it looks, but I was just sort of curious.
But the underlying type theory is similar, right? It's close to Lean. But they have more exotic types. You have these inductive recursive types or inductive. And I see people talking about these things on the Lean chat, and you kind of think, oh, they sound interesting, higher inductive types or whatever. But actually, what I realized when I formalized perfectoid spaces was that we don't need any of that stuff. Mathematicians just want structures. You know that? Talking to Sebastian, it was quite interesting. I said, you know what, we never use induction. And he was like, oh, of course you use the natural numbers. And I'm just thinking, I don't think we do use the natural numbers. Not in the definition of a perfectoid space. We don't need natural numbers. There's no numbers involved. There's a prime number at some point later on in the theory. But we're dealing with complicated objects which are typically infinite dimensional. There's no numbers involved at all in our number theory. That's what number theory has become. So, sort of funny. So I don't need what Agda has to offer. Hello.
So I wrote a paper a few years ago about some folks who had done a formal proof software for Euclidean geometry.
Oh yeah.
And one of the things that they found was when they went and took all of the supposedly rigorous proofs using Hilbert's axioms that were designed to get all of the geometric intuitions out of Euclid, they found that in fact they had subtly carried over a lot of those intuitions and found a bunch of holes.
Yeah,
so I'm curious, with your students doing number theory, did they find a lot of systematic holes in the proofs that appeared in their textbooks?
They find omissions, but an omission is fine, right? That's the difficult thing. When you're a PhD student, you're reading a paper and you don't understand it. It's just because they left a gap that you can't traverse yourself. But you ask you ask your PhD advisor, and they just say, well, you just do this, this, and this. You just do the standard technique. And that's interesting because very early on it gets drilled into your head that if you don't understand something, it's probably your fault. And it was only once I've been in the game for about 10, 15 years that I realized that actually if I don't understand something, it might be because it's wrong. It might be because the people that are writing the paper might not actually understand the subjects as well as I do. But that's not the philosophy. Mistakes are normal. They're a part of, I got one of my summer students formalized all of that Euclidean stuff. Wrote hundreds of lines of Lean code formalizing Hilbert's axioms. They proved a whole bunch of stuff. It was amazing. It was one of the many things we learned. All unpublished, all on some private GitHub repository, completely unavailable. But it's one of the many things we... Yeah, sure, there's mistakes. But we know how to... The undergraduate level, we know how to fix them. Right, at the research level, some of them really are mistakes. But that's normal. You get away with it. That's the point. You get away with it. So it doesn't bother me. Hello.
So kind of related to my earlier question, one thing I've been thinking about is you've been talking about the different systems, and then as well as how the proof development in the English or French or any other language prose would pair with that and be communicated. In some sense, the thing you might want to share wouldn't be, say, a Lean proof development or Coq proof development, but what is generated from that, and ideally checked by many different systems.
Oh, that would be nice.
As a mathematician, do you care that a particular proof development, if you sat down and read it, maybe stepped through it line by line, the prover actually carried any kind of human level semantic content, or do you want that alongside some documentation? And those things can also drift sometimes, say in regular programming. So what do you think about that? in terms of a future for using proving?
So I've talked to a lot of people, a lot of mathematicians about what a proof is and what they want from a proof. And I'm a formalist. So as far as I'm concerned, if some computer came up and generated a 1 billion line long proof of the Riemann hypothesis in some type theory that could be formally checked to be correct, but gave us no understanding at all, I'd be super excited about that. But I know a whole bunch of people that would be super, super cross or might even reject it. So within the community, there's huge diversity of opinions as to whether we care about semantic content of a proof. But actually, talking to Leo and Daniel this week, I did realise that I'm very selective about which proofs I read. I tend to only read proofs if I think if I want to know what the idea is. Because that's all, 99% of what's published is mathematicians just generalising ideas that they've learned in other places and applying them in either different situations or slightly more general situations. So you have to learn some proofs. But I don't know, we've got... Yeah, I'm torn. The formalist part of me says, I don't care. Right? I just think, why don't we just make computers do it all? Then we don't have to worry. No human understands how their phone works, right? Or most humans don't understand how their phone works. Do we really need to understand how maths works? And then on other days, I kind of think, well, actually, that's the point. There's loads of different answers to your question. I personally am a formalist, but I know people that would actively be cross if you suggested that we should start taking proofs away from them. Because for them, the beauty is the idea, and the idea can get lost. But beauty is one thing, and truth is another thing. And I'm kind of more worried about truth. That's why I'm here. And I've met mathematicians that say that you shouldn't believe any of their papers. Their papers are just telling stories. And that, you should enjoy the beauty of the story. And they don't really care if it's right. I mean, they know they've got it past the system, so they can put it on their CV. But, if somebody told them that their theorem was wrong, they wouldn't be too bothered. It's extraordinary, the people, when you actually start asking delicate questions. Some people just aren't, they claim that they don't really even care if they're right or wrong. It's just, the fun is the ideas. And that's what we're doing. We're just passing around abstract ideas. Yeah, because abstract maths is beautiful, right? A perfectoid space is a really beautiful thing if you're one of the very small number of people that can understand it. So funny. Yeah, I don't know. I reject beauty. I want rigour. But not all of us do. Is that an answer? I don't know. Hello.
Have you tried selling this to theoretical computer scientists?
I thought that was you guys. Yeah, I've spoken I'm speaking at something called ITP next week. Yeah, in Portland, Oregon. And I think that'll be full of theoretical computer scientists. So yeah, I do talk to them sometimes, but I mostly talk to mathematicians. Yeah, what should I tell them? Are you a theoretical computer scientist? Oh, okay. Yeah, what do they want to hear?
They'll love this.
Okay, great. Because the mathematicians are skeptical, but yeah, I don't know where I am. I'm between the cracks now. I want to just make lots and lots of noise until somebody eventually realises that what I'm doing is important, if it turns out to be important. But am I crazy? Surely this stuff will have an impact in my area. Isn't that obvious? It's so obvious to me. It must inevitably have an impact in my area. Right? It's why that's the selling point. I just need to convince people. But my impression is that theoretical computer scientists have kind of taken it as far as they want. It's great. They've done the odd order theorem. They've done loads of stuff, but now someone else has to have a go. That's my impression. I think they know that their software is great. Maybe I don't know. They're interesting to talk to. They ask me weird questions. They start asking me about how I come up with ideas and things. I spent 20 years talking to number theorists, and we talk about technical number theory. And now all of a sudden I'm talking to people that are asking me really weird questions about the process I go through when I'm doing mathematics. So it's really interesting talking to a new group of intelligent people.